Using this from a probabilistic perspective. So I will talk to what probabilistic is as I go through the presentation. For those who are not familiar with Pourbaix diagrams, let's talk about its structure. It's a very simple diagram with potential on the y-axis and pH on the x-axis, and we do have like a lot of different lines, some vertical, some horizontal, and these lines come out of the North equation. And depending on whether the line or depending on the electrochemical reaction that has proton or electron, it has like a different lines. Like if it has both proton and electron accent, we will get a diagonal line. And if it has got the proton accents only, we will observe the vertical line. And if it is electron accents only, we will observe the horizontal line. And there is hydrogen evolution reaction below that blue line, and the oxygen evolution reaction above that orange line. Moving on, let's talk about why do we need to care about Pourbaix diagrams. Is it because it gives us an idea of whether the particular metal that we are interested in is stable or not. So sometimes the metal could be in the solution and it gets dissolved, affecting our electrode and a lot of different chemical experiments. And Pourbaix diagrams could be useful for us to identify whether our metal is stable or is it corroded, that it has already dissolved in the solution or it gets changed into different forms. Likewise, sometimes if it is at higher pH, metal gets changed into hydroxide, and we need to know information about that as well. And since Pourbaix diagram helps us to understand that, it has been used in various applications. As you can see, corrosion engineering, battery and fuel, hydrometallurgy, electrodeposition, and also in electrocatalyst. But there have been three different challenges with Pourbaix diagrams. The first one is that the Pourbaix diagram that we see on materials project or any other different sources are limited to metals or metal alloys. But in our real experiments, we do add complexing agents to it. So when complexing agents are added, then the traditional Pourbaix diagram do not have that. The next one is we assume like a fixed activity of metal when we construct the Pourbaix diagrams. But the activity during complexation changes a lot at different pH. So that is another limitation of existing Pourbaix diagrams. Moving on, the Pourbaix diagrams are generally constructed from equilibrium constant, and if we see different literature, it varies a lot. Somebody reports and has a lot of variability, as you can see on the screen. The KSP value of nickel hydroxide, nickel is something that we are interested in, ranges from 10.99 to 18.06, and this is in log scale, so it is in order of magnitude variation. So how do we tackle this problem? First, we believe that we need to solve for dissociation first. That is, we need to account for the thermodynamic and mass balance that determines what the activity of the pure metal will be, and then we need to take that to the Nernst equation. That is the first approach we use it on. And the next one is for addressing the variability in the system, we do it by Monte Carlo simulation. That is, rather than taking one specific value, we take a range and analyze the Pourbaix diagrams based on that. So, for this specific case, I would like to highlight on the nickel Pourbaix diagrams with complexing agent, just because Paul Sabatier said that if we change the preparation condition for nickel electrode, it can be a workhorse. And he has said that it can do a lot of different works and have activity for a long time. But nickel is carcinogenic, it might not be a good idea to spray coat it, so we are more interested in electrodeposition to produce probably the workers, and electrocatalysis where we are most interested in. So, but nickel electrodeposition comes with a challenge as well. If we want to operate it in lower pH, there is a lot of hydrogen evolution reaction. That means we will have very poor deposits. And if we were to do it at higher pH, that it forms like insulating nickel hydroxide. And if nickel hydroxide forms, it's insulating and we cannot get our electrodeposit. So we have got a very small window, but the idea is to move this to the right, so we have a bigger window for the electrodeposition, and it offers more flexibility. As we go through the basic condition, we suppress hydrogen evolution reaction as well. But how do we move this boundary to the right? The answer is complexing agent, and to produce the workers, we need complexing agent like ammonia or citric acid. They have been reported in the literature, but the quantity on how much complexing agent should get into the back, whereas also how much would this complexing agent shift the nickel electrodeposition window is not known. So in order to know that, one way would be to do a lot of experiments, try it out at different concentration in the lab. You might be able to probably get it. the next way is to do thermodynamic modeling, and this is what we are interested in. Now, as I pointed out, in order to solve for the Pourbaix diagrams, we should first solve the speciation diagram. And in order to show this, I'm showing the speciation plot of nickel ammonia at 1:10. We are having 10 moles of ammonia higher than that of nickel, and at different pH, we do have a different activity of metal that we are interested in. If we get like 0 to 6, nickel dominates, and then the amine complex. Ammonia, nickel forms different ammonia complex, nickel binds with 1 to 6 different amine groups and forms different complexes. So 1, 2, 3, 4, 5, and 6. These are the ammonia complexes that dominate at different pH. And then finally, we have nickel hydroxide. So this is the speciation-aware Pourbaix diagrams. That is, we solve the speciation first and then draw the Pourbaix diagram. So depending on how much ammonia you have, the Pourbaix diagrams could look different, and the window could be shifted to the right. Also, as the activity changes when we have complexation, you can see that there is a curved species there is a curved lines on the Pourbaix diagrams, as you can see on the screen. Similar observation is observed when we have citrate in the system. It also does the job compared to the ammonia, which we're having at 20 moles higher than that of nickel, but citrate can achieve same thing at very less concentration, because nickel had to combine like 6 different ammonia or 5 different ammonia to it, but nickel complex can be quite easier with lesser concentration. So, okay, how do we handle the uncertainty or the thermodynamic variability? The one way would be to the existing way is deterministic. Since there are a lot of values in the literature that varies a lot, we take one of it, fit it in the model, take one output. But what we are interested in is, for all the uncertain variable, let's calculate the probability distribution function for that particular variable, fit to the model. Instead of getting one value, now we get the range of different outputs. So we are more interested in getting the probability of something, or probability distribution function, as you can see on this meme. We love probability distribution function, and that's what, so we need to operate on the region where we do have like higher confidence zone. And this is the Monte Carlo simulation. So once we have like 10,000 to 1,000 to 10,000 different experiments we did on the model, and we see the region, rather than having a discriminating thick line, we do observe like a pattern or the spectrum of that colors at the different rays. And through this, we can plot the probabilistic or uncertainty-aware Pourbaix diagrams, and we do have different confidence interval at different regions. And so when will nickel precipitate? Instead of saying that nickel will precipitate at certain pH like 8.9, which is a deterministic way of saying, we can rather say that through Monte Carlo simple technique, we got that nickel will precipitate from pH 6 to 11, depending on the thermodynamic value that we use. So the conclusions that I want to draw is that for drawing the Pourbaix diagram, since the activity change, we need to account for speciation. And for any experiments that you do, you should be asking yourself, what is the probability of me getting the same thing again? Is it 100%? If not, then you should be doing probabilistic analysis on that. And for whenever we have to design our experiments based on for different metals, we need to use a region where we do have like a higher confidence. That said, I would like to acknowledge Imperial College London, CDT in Green Industrial Future, and my amazing supervisors, Anna Hankin and Professor Ifan Stephens, and our collaborator, Dr. Isaac, and all members from Electrochemical Systems Laboratory and Electrochemical Group at Imperial College London. So you can access the resource. I have the deployed model is live. You can access the GitHub, and also this, whatever I've said, all the modeling techniques and how it is modeled is also available in the YouTube, so you can. And if there is any questions further, I'll be happy to answer them. Thank you so much. Is there any questions?
Thank you for your presentation. I'm wondering if you also consider the other complex for like citrate and ammonia on the nickel, because in your case you already have a nickel complex with ammonia and citrate, right? Do you also consider the complex of nickel, citrate, and ammonia?
No, currently it is not considered, and it would be more realistic to consider that. But because like we do lack the nickel citrate ammonia complex thermodynamic values, we could not include that, but it would be more useful to include that, and it will make the realistic system even better. So thank you for drawing that attention. Yeah, thank you so much.
Any other questions?
Yes, what is the amount of experiments you need to validate your model?
So we have not done the experiments to validate the model. This is completely like thermodynamic analysis. But what we have observed is that people have done electrodeposition experiments, putting the citrate and ammonia as complexing agent, and they are doing electrodeposition at around 10 pH. So, and this sort of validates the secondary sources that we have. But in our lab, we have not done the experimental results to validate these results. Yeah, thank you. Yes, please.
Be interested to know how sort of applicable would this be to other metals? Is the approach sort of easy to apply to other metals?
Yeah, so our main goal is to have a database for all the useful metals like nickel, platinum. That is the goal. But since for different metals, different complexing agents would be needed, so we would need the thermodynamic values or their solubility limits or those kind of constants in order to make that. But once it is done, we can extend. The idea is to extend it to other metals as well.
Any other questions?
No, it's very interesting talk. So one question, how do you estimate the uncertainty, and what are your assumptions on the uncertainties of the actual experimental data? Are you assuming they're uncorrelated, or?
So what we found is, so in order to draw these diagrams, what we need is the thermodynamic constants, and let me show you. Yeah, so these are the different constant values, and we had to get it through different literature. And looking at the literature, as you can see, I have like minimum and maximum written. So in different papers, we have different values of this. So we were interested in, okay, let's merge it together and see the overall spectrum of what it is, because each value you choose will get different Pourbaix diagrams, or different speciation diagrams. So we were not sure. So this is the secondary data that we have, and we're trying to look into like considering all of them and seeing the uncertainty of what it could be. So we analyze it based on that.
But could it be that because they don't really measure these equilibrium constants, they actually measure species and then fit the equilibrium constants, that actually these errors in the different equilibrium constants could actually be very correlated?
Yes, exactly. So because, and the reason is because these equilibrium constants are like actually measured in labs through different methods, and doing it through different methods, we get different values, and that's why there is uncertainty in like these values. So we need to analyze it in terms of probability rather than actual value, because we are not sure what the actual value is, or getting it in the lab might be different, and it would be like experimentally very expensive probably. So we had to rely on the data that we have, and this that we created the model.
Okay, so no, very, very nice work. Thank the speaker.
Yep. Thank you.